So in this video, I'm going to go through proportions with volume, section 11.6. So if we take two similar cylinders, or really two similar any three-dimensional shapes, what we're going to do is investigate and find their volumes and then compare the ratio of the smaller one to the larger, do the same thing with the height and the radii, and see if we can find a relationship. So the height of the small one is 5, the radius is 3. So if we plug that into our formula, pi r squared h for the volume, the small one is going to be 45 pi, because 3 squared is 9, 9 times 5 is 45. Now we do that with the ratio of the large one, so 10 and 6. So we do 6 squared times 10, which is 360. Okay, so then to cancel this out to see a pattern here, pi's cancel out, and 45 goes into 360 exactly 8 times. So then if we compare the small radius to the large radius, we see it's the same as the small height to the large height, which is 1/2. Okay, maybe you noticed, this kind of halving relationship or doubling relationship, but if we compare these numbers, they're not just 2 times each other. It's actually this value times itself 3 times, because 1/2 times 1/2 times 1/2 is 1/8. So we see this kind of a similar relationship that we saw with volume, only this time we're raising the corresponding lengths to the third power. So here's the formula, again, similar to what we found before. The corresponding edge lengths, radii, heights, etc., could be any lengths I give you. That's m and n. We put those in a ratio and we raise it to the third power. And then the ratio of their volumes will be equal to that. So just like before, the ratio of the radii was 1/2. So if I cube that, I get the ratio of the volumes. Okay, so example, we're given these pentagonal pyramids. We're given the volume of the small one. We don't know the volume of the large one. That's what we have to find. And we're just given that the height, this height is 4 and this height is 7, but we're missing anything about this base, which is what we would need to know to actually calculate the area. We don't have that, so we can't use that. So instead we're going to use our formula, set up and set it up. So the 4 over the 7 goes in for the m and the n, and then the volume of the small goes on the top, volume of the large goes on the bottom. And now we could type this whole thing into our calculator, but we're going to get this really nasty decimal. That's going to be hard to work with. You're going to have to round it off, and then your whole answer will be off by a little bit. So instead, I'm going to keep the fraction and instead raise the numerator to the third power and the denominator to the third power and write it like this. Oops, that should be 320. So now I can cross multiply and divide. So 343 times 320 equals 64 times v, and then divide by 64, and you should get 1,715 for, let's go ahead and do centimeters cubed, and that is the process for this. So really similar to the area formula and the process we did in section 11.5. Okay, one more example with similar cones, and now again, it's kind of working backwards. We're told the ratio of the volumes, so that goes in here. And we're missing one of these radii. And of course, we don't know the heights of these, which is a missing element because the formula for a cone is pi r squared h over 3. We can't find the volume. Like if we just know the radius, there's no way to find the volume. We need to know the height as well, or we at least need to know this height. This length, I mean, and we don't either. So instead I'm going to plug in, the one we're missing is clearly the smaller one, so that goes on top. The 4 goes on the bottom, so that's replacing this part of the formula, and then cube to the third power. Then the volume of the small one is 27. Volume of the large one is 64. And actually, we're just told that they have a ratio. We're not told explicitly that these are the volumes. They could be bigger than this. So now to solve this, we want to just take the cube root of both sides. Okay, and so we're just asking what times itself 3 times is 27. So that's 3. And what times itself 3 times is 64. That's 4. And now we can clearly see the radius must be 3. Because if these are both equal, this r must be there. If you cross multiply, 3 times 4 equals 4r, you're going to see the same thing. Just to take you a little bit longer to see it. Okay, so if you're given the ratio of the volumes, a shortcut would just to be take that fraction and do the cube root to, and then you can figure out that must be equal to the ratio of these two radii. Or I could have given you these heights as well. So that's it for 11.6. Thanks for watching.